Video problem 70, properties of solutions. Determine the change in boiling point and freezing point. So I'm looking for the delta TB and then the delta TF, which is just the change, for a solution made of 0.22 molal glycerol in ethanol. And then I'm given a Kb and a Kf value. Now these values here, the Kb and the Kf, those are specific to ethanol. Okay? So what we're doing is we're looking for the change in the boiling and freezing point of ethanol. Not the new boiling and freezing point. We'll do a problem like that next. So I'm going to use two different equations. The first equation is delta TB is equal to Kb times M times I. And then the other equation is delta TF, is equal to Kf times M times I. Right? So let's deal with the change in boiling point, delta TB. It's going to be Kb, which is 1.22 degrees Celsius per molal, times the molality, which is 0.22, times I. Now I is the number of ions that it breaks up into. Glycerol is not ionic, so it doesn't break up into ions, so that's a 1. Right? So that value ends up being 0.268. So that's the change in boiling point. Okay. And we'll talk about that here in a second. So let's do this one over here. The Kf is 1.99 times 0.22, and again the I is only 1 because it doesn't break up into ions. So this ends up being 0.438. Now both of these should be 2 sig figs. Okay, so 0.27, 0.44. Now what this means is that the boiling point will increase, and we're talking about the boiling point of ethanol here, the solvent. It'll increase by 0.27 degrees Celsius. So for the freezing point, that's how much it will decrease. So it'll decrease by 0.44 degrees Celsius. Let's try one more. Determine the new boiling point. So now I am actually looking for the boiling point and the freezing point. If 3.50 grams of sodium hydroxide is dissolved in 175 grams of water. Here's the Kb of water. For some reason I didn't give the Kf in this problem. There's the Kf. So you might want to jot that down. Okay. So again, first I'm going to have to find the new boiling point or the new freezing point. But even before that, I'm going to have to find the molality, because I'm going to use this equation, delta TB is equal to Kb times M times I, and then I'm also going to use this equation, delta TF is equal to Kf times M times I. Right? But in each case I need the molality, and of course we know that that's moles of solute per kilograms of solvent. So my moles of solute is going to be 3.50 grams of sodium hydroxide (1 mole). Sodium hydroxide, let's see, I guess I should get the exact value, huh? So sodium is 22.99. So I get a value of 39.998 grams. So that leaves my moles at 0.0875. So there's my moles of sodium hydroxide. Now if I want to calculate the molality, I'm going to take that value divided by 0.175, because that's my kilograms of solvent. So that gives me a value of 0.500. Right. So now I can plug that value into here. So I'm still looking for delta TB. The Kb of water is 0.51, and And again, that's just a value you can look up into text. Molality is 0.5. Now the I, now we're dealing with sodium hydroxide. And sodium hydroxide in water breaks up into ions, like this. Okay, so that means we get an I, a Van 't Hoff factor of 2. Now in reality, it's not actually 2, it's really close to 2. It's like 1.8, 1.9, something like that. And again, that's a value that you can actually look up. So for that, I got 0.51. Now that's the change in boiling point. That's not the actual new boiling point. Okay, so what I can do here is now I can take my delta TB. And delta TB is always the boiling point final minus the boiling point initial. Right? So the delta TB, which is 0.51, is equal to the boiling point final, which is what we're looking for, minus 100, because that's the initial boiling point of water. So I'm going to add 100 to both sides, so I end up with 100.51 degrees Celsius. So there's the new boiling point. I'm going to do the same thing with the freezing point, just use the different numbers. The molality is still 0.5. The I is still going to be 2. So I get a value of 1.86 degrees Celsius. So again, I can use this to calculate the new freezing point. So what I get? I got 1.86 is equal to temperature final, which is what I'm looking for, minus 0 degrees Celsius. Oh, we got a problem here, don't we? This should be initial, but I still see a problem, right? Because this is saying it's going to go up to 1.86, and that's not true. So I have to do something different here. You know what, let's do this. We know it's going to drop by that amount, right? So negative 1.86 degrees Celsius is the freezing point final. Okay. So this value, this change in freezing point, we know it's going to drop by 1.86, so that's why I made it a negative. If you wanted to, you can go back and adjust this. To look like that, and you're going to end up with the same value.